Fuel air cycles. Air standard cycle has highly simplified approximations. Therefore, estimate of engine performance is much higher than the actual performance. For example, actual indicated thermal efficiency of a petrol engine for the compression ratio 7 is around 30%, whereas the air standard efficiency is around 55%. So this large difference is due to non-instantaneous burning of charge, incomplete combustion, and the largely oversimplification in using values of properties of the working fluid for the analysis. So in standard air cycle, it was assumed that the working fluid was air which behaves like a perfect gas and had constant specific heats. In actual engine, the working fluid is not only the air, but a mixture of air and fuel and the residual gases. Also, specific heats of working fluid are not constant, but increase as the temperature rises. And products of combustion are subjected to dissociation at high temperatures. Engine operation is never frictionless. Theoretical fuel air cycles which take into account the variations of specific heats, effect of molecular structure, effect of composition of mixture of fuel and air, residual gases approximation are called the fuel air cycle where we consider all the things. Fuel air cycle largely take the following into consideration: actual composition of the cylinder gases, that is fuel, air, water vapor and residual gases, variation increase of specific heat with the temperature. With the temperature, the specific heat rises. Specific heat vary or it increase with the increase in temperature. Hence, gamma is equal to Cp by Cv. The ratio reduces with increase in the temperature. Cp is equal to A plus Bt plus Ct square plus Dt cube. Cv is equal to A1 plus Bt plus Ct square plus Dt cube, where A1 is greater than A. Theoretical fuel air cycle will see the mixture of fuel and air. After combustion process, mixture is in chemical equilibrium, no dissociation. Intake and exhaust processes takes place at atmospheric pressure. These are the theoretical assumptions actually, not the actual one. Compression and expansion processes are adiabatic without any friction. In case of Otto cycle, mixture of air and fuel is homogeneous and it burns at constant volume. No heat exchange between gases and cylindrical walls. Change in kinetic energy is negligible. Now we'll see the theoretical fuel air cycle. The first point, effect of composition of fuel and air ratio. So if the mixture is leaner, we'll get higher thermal efficiency. If the mixture is rich, then we are getting the lower efficiency, as the unburnt fuel is actually expelled to the atmosphere through the exhaust. Efficiency increases with the compression ratio. So efficiency of the Otto cycle, we know the formula. Efficiency of diesel, we know the formula. So from the graph also it's very much clear that the leaner mixture have the greater thermal efficiency, whereas the richer mixture have the lowest thermal efficiency. Effect of variation of specific heat. So if we observe from the graph that ideal Otto cycle is from 1, 2, 3, 4. So we'll see 1, 2, 3 and 4. This is the ideal cycle. Whereas the actual cycle, if we observe 1, 2 dash, 3 dash, 4 dash. So see 1, 2 dash where the pressure is bit lower compared to the ideal one, where 2 dash, then 3 dash, 4 dash, 4 double dash and 1. So this is the actual cycle. Now, effect of variation in the specific heat, we have already gone through it. It is clear from the curve.